I'm just going to get going. So yeah, welcome to Lambda Montreal, May 2017. That's a typo. So I'm going to talk to you about syntax parse. And before we dive in, I just want to survey people's knowledge of things like Common Lisp. Has anyone programmed in Common Lisp? Okay, most of you. Awesome. How about something like scheme flavored? Oh, awesome. Cool. Particularly Racket. Has anyone messed around? Cool. And there's also other. Has anyone messed with Clojure or Lisp flavored Erlang, Emacs Lisp? I imagine people have messed with Emacs Lisp. Okay, cool. So you guys are a Lisp crowd, which is exciting. I'm probably going to be wrong, so I anticipate corrections. So syntax parse is basically this new domain-specific language for writing robust macros in Racket. Mainly, it uses a declarative sort of language as well as giving you the ability to define certain shapes and types of syntax that you expect in order to generate helpful error messages. So this is implemented in Racket. I recently discovered it's also implemented in Guile scheme, if you guys use that at all. Racket, formerly known as the LT scheme, kind of grew out of the scheme implementation into its own thing. It specifically targets itself at helping developers create new programming languages. The basic gist of it is that you have all of these different languages implemented in Racket, and individual modules can work together in a seamless fashion, which is pretty nice. That means you can have, let's say, a domain-specific language for typesetting your documentation, and in that you can have inline code that gets evaluated, sort of like literate programming. That's Scribble. They're also working with a gradually typed version of Racket, which is kind of fun. Someone else is implementing a Haskell clone. There's also plain scheme implementation. And they also have other fun kinds of languages, like they have a language for functionally describing pictures, and out of that grew this slideshow language, which is what I typeset this presentation in, and many more other languages. Basically, anyone who wants to mess around trying out some new paradigm or some new way of expressing a certain problem is invited to use Racket. So I'm just going to really briefly gloss over this. This is Lisp syntax. Everything is a list. Everything is also an expression. Some expressions are quoted. Do you guys see the little point? Okay. And there's also certain parts that can get unquoted. For example, here's your little backtick, which represents quasi-quote. And you can have symbols that are unquoted, and then they get replaced with the binding for that value. So for example, this will return a list that says simple x has value 5. We also have lambda functions, and we have functions that take other functions as arguments, meaning this is a functional programming language. Okay, so we're talking about writing robust macros. A macro, short for macro instruction, is basically just something that gets replaced by some other thing, usually at compile time. Most languages just do plain text. Other things have syntax objects, like Racket. So, you can see we have this sort of brittle macro facility where they basically will inline every instance of this min call with this ternary operation that will compare the terms and return the one that's smaller. Unfortunately, you can also use this in sort of dangerous situations. Like, it is valid syntax to use that as an if, like if min something. So you can get weird things with C macros. Erlang has a similar sort of thing. We define this trace macro, which just literally prints where we are in a particular module and what line, and then what thing we want to print. And in Lisp, we have this def macro thing, which will basically is more or less a function that accepts syntax, and then it produces syntax, which is kind of really cool because you get this moment where you start writing a program to write your program. So for example, this when macro gets expanded to this if expression, which evaluates the condition arguments, and it also brings in the body arguments. And if that's a list, it sort of splices it into this prog n expression. So we have when, this is your condition, and this is your body. It gets expanded to a nice if expression, and everyone's happy. Okay, so the problem with writing macros is that they tend to be very brittle. When you're extending a language with macros, it's very often the case that you will have a well-formed macro that will expand to code that just breaks at runtime, and debugging that can be kind of tricky. And also adding error reporting to your macro is tedious and will generally clutter your code significantly. So that's what syntax-parse tries to fix, right? So we have macros that are brittle and readable, or robust and unreadable, and then syntax-parse tries to bridge that gap by giving us readable yet robust macros. So for example, we have this set q if true macro. Basically, if this evaluates to true, we're going to set this symbol to the value that gets evaluated. So if we have this variable foo, and if we want to set it to 17, or rather, we'll set it to 17. 17 evaluates to true in common Lisp. So at the end, we have foo set to 17. What if we, so now this temp symbol is, it can be overwritten, or rather, this temp symbol can be overwritten in this case where we have a let statement. And effectively what the macro does is it updates the value from the let statement rather than the value you defined here. So this is called variable capture, and it's mostly a solved problem with this new thing called gensim, which produces a symbol that you can then bind things to, and then nothing will ever sort of tamper with that. So this is the same macro, but using gensim, and it will do the right thing in our previous example. It will set this temp rather than the other one. Unfortunately, that solves, some issues, mainly variable capture. However, what gensim can't really protect, or what Lisp macros can't really protect against, is free variables in the macro template. So we have this push if. Again, I'm using conditionals here. If this condition is true, we're going to push something onto the stack. If we have this thing named stack, we kind of have the same problem. So Scheme set out to fix problems like this by introducing what's known as hygienic macros. And so basically, these are definitions more or less copied from the Scheme specification. Whenever a macro has this binding to an identifier, the identifier is renamed in the macro. So you get gensim baked in for free. And then if a macro inserts a reference to an identifier, like what we had with stack before, that reference will always refer to the binding that's visible where the macro is defined. So I kind of think of it as looking as a sort of difference between dynamic scoping and lexical scoping. For example, here the stack symbol is bound to AB, and this macro will sort of replace stack with what is most recently bound to it, rather than what is bound at the definition site of the macro, which is up here. So, that's how I like to think about it. It's possibly wrong, but I find it helps. So Scheme has these hygienic macros. It was introduced in, I think, R5 RS with this form called syntax rules. And it basically gave scheme programmers this simple sort of pattern language where you match macro invocations to certain patterns and those turn into different templates. So it's still kind of brittle, and although hygiene is great, we still have this issue that we have good macros that turn into bad code at runtime. So we need some way of checking whether a macro invocation is correct at expansion time rather than at runtime. And what we want most of all is a good error message. So here's a sort of basic syntax rules style macro. We have this let, and then we say, okay, we have a list, a bunch of 0 or more pairs, and we bind the first and second thing to var on the right-hand side. And then we have 0 or more body expressions, and it basically creates a little lambda closure and then applies the right-hand side to various variables. So when we try to use it in a bad way, for example, by putting the right-hand side before the variable, we get this lambda error, which doesn't exactly tell you what is happening. It just says not an identifier. It doesn't exactly pinpoint where. So in comes syntax-parse. Now we're going to look at syntax-parse macros for this same kind of mylet version. So do you want me to go back to a particular slide? Okay. So recapping, these are the problems that we have with macros. So as I mentioned before, syntax-parse has this more expressive, more sort of sadistic language for describing the types of macros that you want to see. And it will basically give you automatic error reporting. You just need to say, you need to name the shapes of syntax that you expect. Okay. So right, these shapes of syntax are called syntax classes, and these can be annotated with various guard conditions that will produce an error when things fail to meet those conditions. And by having these, we have these sort of reusable shapes of syntax that will give good error messages to bad invocations of macros written with syntax-parse. I'm not going to talk about that. So it looks more or less the same as what we had before with the syntax rules, because it largely is the same. We still have these things that get bound, and that's the expansion. But what happens is that we have this sort of sugar here with the colon, and then this ID or this EXPR. That says that I'm expecting var to be an ID, like an identifier, and I'm expecting the right-hand side to be an expression. And then once those things happen, you can expand to the proper expansion. Yes?
What is the plus?
The plus means one or more. It, like the star in regular expressions, plus. Okay, so when we try to use something that's not an expression, where syntax-parse will expect an expression, it'll actually tell you, hey, this is bad. I expected an expression. Now we can do more than just that. Oh, right. Another example is if you put something that's not an identifier where it expects an identifier, it'll let you know. So already this is a massive kind of improvement over the previous macros that we were using, but it gets better. So this pattern of having some identifier and some expression is something that we can reuse all over the place. Anywhere that will turn into some sort of closure, we have this list of binding pairs. So we can define a syntax class for it, and we'll name it a binding pair, and this is the pattern we'll expect. And now when we're writing our macro pattern, we say we expect 0 or more bindings. And then the error messages get slightly better. for other types of misuses. So this now says that it expects a binding pair rather than just a flat list. And then once we have this list of binding pairs, we want to make sure that we're not accidentally writing over a particular binding twice. For example, if we have let A5 and then or A7, that should be an error that can be caught at expansion time. So we're going to add this fail when clause. These are built-in Racket functions saying, hey, check if there's any duplicate identifiers in this list here. And if there is, it will tell you duplicate variable name as your error message. So here we have this exact issue, and it tells you exactly what the problem is. And we literally had to just, very little to get that built in, and that will work, and it's reusable. Well, it's not reusable yet. Let's make it reusable. So now we can have this new syntax class called distinct bindings. And this is just sort of encapsulating what we had before in the pattern, but now we're making it reusable, where we have this list of bindings as the pattern, and we have this side condition and the error message that gets reported, and then for convenience we can actually bind. These are just extra little binding pieces of sugar for here. That basically says you can refer to the variable inside this syntax definition or the right-hand side. So now we have this robust macro that with 15 or 16 lines of code that catches most erroneous invocations for you and will give you a helpful error message. But there's more. In addition to regular let expressions, there's also this idea of a named let expression, where you will name sort of the body part of your let expression. You'll give that a name and you can call itself. And this will give you sort of easy recursion in your let expressions. So what we just do is we add this new pattern and we say, oh, we can also expect the second term to be an identifier. And then we have our distinct bindings. And then we have a series of body expressions. And we have slightly different expansion for that. And now we have named lets with our macros. And our error messages also get better when we have more patterns. For example, for these completely erroneous invocations of this macro, syntax-parse will generate a nice error message saying, hey, I expected some identifier or a sequence of distinct binding pairs, but instead you gave me this. And that was generated sort of automatically based on how syntax-parse matches the input syntax to your macro. Basically, when you have multiple patterns, and if it parses, let's say, the first thing, and then the second thing that it expects is either a list of distinct bindings, or in this example, an identifier, it will say it expects one of those two things. And that's basically a very easy way to get clear error messages for any weird kind of macro invocation you want. And, for example, this gets read as an identifier, and it just tells you that you need more terms after that. So yeah, what if now I want, let's say, Clojure let expressions? You don't need to have these pairs wrapped in parentheses. You can just say let A1, B2, C3. You don't have to type those 6 parens, and it gets parsed fine. Maybe I want that kind of sugar in my language, and I have macros, so I can make it happen. So the next really big, cool thing that syntax-parse gives you is this sort of pattern language for describing patterns. There won't be really any of these in the presentation after this, but it's worth checking out if you are interested in looking into it. So we say, I expect a sequence of identifiers and right-hand side expressions, and that just basically means it's not wrapped in a list. This gets spliced into where it gets expected, for example, here and here. And so now, when I use my Clojure-style bindings, it works the way it should. Unfortunately, we gave up what we had before, like with our regular let expression bindings. If you want both, you can have both. So we could just redefine binding to be either a pair of two elements, an identifier and a right-hand side expression, or we can define it to be just an identifier and a right-hand side expression, but without the parentheses around it. So we have this or, which does exactly what we want, and that's it. And everything else is literally the exact same. And now we have both at the same time. And great. Sort of the other example that I prepared and found this afternoon was that OR is a macro in Racket, and macros can't be used sort of like a normal function. For example, if we're applying OR to this list of values that's bad syntax, instead you should use something like OR map. They have forms that sort of let you get around that. Or you can define your own function for it. But with syntax-parse, we can basically give ourselves a first-class OR macro. The invocation of this macro has three different shapes. If it's just alone in an expression, it's false. That's sort of the default behavior for OR. If it's a list, then it turns into an if expression and then a recursive call to the macro. And then we have this other thing, now that we can say, oh, this is being used as an identifier, we can replace it with a lambda function, which is exactly what we would supply to some function like apply. So the general, okay, so syntax-parse is used quite a lot in the Racket code base. I think the most interesting use of it is for its pattern matching library. I mean, it makes sense because syntax-parse is basically pattern matching for you with a very, very expressive, big pattern language that you can use really nicely. Racket is sort of Racket's build tool. That's what you can use it to fetch packages from their own package repository. What sets up new projects for you. It's a lot like Cargo for Rust. And that also uses syntax-parse for handling commands and arguments to it, which is kind of cool because it's just a regular terminal application. The current paper that I'm slowly digesting shows off this new language called Clojure-style, which basically lets you write a typed language in Racket. And this is kind of a huge deal because typed Racket produces, well, the way that typed Racket goes about being a typed language in Racket is that it will first read your program. Well, I don't know enough about typed Racket to say that. This will let you basically write your own type checker fairly easily. I highly suggest you check out the paper because you basically use, I think it's judgment syntax, where you have your symbols and like the turn style itself. You can write all that in Racket, and then you get a typed language as a result. I look forward to playing with that, but I really don't know anything else about it. But yeah, that's sort of become the de facto tool for writing macros in Racket, just because you get nice error reporting for free, and you don't have to write exhaustive error checking into your macros. And yeah, It's powerful, and if you ever feel like designing languages and you want to write macros and stuff, you should try Racket and syntax-parse. Right. Further reading, we have this fear of macros. Basically builds up how to write scheme macros from their sort of syntax objects. And the last chapter is syntax-parse. The paper/PhD thesis chapter that introduced syntax-parse is Fortifying Macros by Brian Culpepper. And if you want to get hyped about what Racket is useful for and all the cool things that it can do, this Racket manifesto is worth a read. And of course, Racket's documentation is, I think, the nicest documentation for any language I've ever seen. It's really quite amazing.
It started as an educational language, I think. So
yes, that's right. Yeah, Scheme sort of emerged out of pedagogy, and Racket did too. Particularly Northeastern universities, sort of where the steering committee for Racket lives, and that's where Brian Culpepper graduated his thesis. So, right, you have excellent documentation in Racket. It's well worth a try.